All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1206. Okay, let's jump right in. Yeah, so yeah, as I mentioned, I'll just make up a class towards the end, asynchronously, probably, if to make up for the class that we missed yesterday because I had an emergency. And yeah, I think that's all I want to say about that. I don't think I have any other announcements. I did miss an appointment with one of you, which we said we'd get to after class. Just to be safe, because things are still a bit scrambled, just shoot me a private message towards the end of class so I actually remember and I don't just go collapse somewhere. And we'll get that done. That being said, we have more notes to talk about for some properties or what derivatives can tell us about curves. I don't really want to open up a new page here. I just kind of want to continue here. So this is going to be, I mean, I could just indicate here that I continued. So continued on today's the 17th. And we'll just pick up right here in the same page. Let's maybe do a little bit of review. Do I have to go back this far? Maybe, yeah, let's just go back. So we did a little bit more work on taking derivatives of inverse functions. I wanted you to know how to differentiate sine inverse and tangent inverse specifically. And we did a bunch of examples from that. And the formulas are here. The derivative of tangent inverse is equal to 1 over 1 plus x squared. And the derivative of sine inverse is equal to 1 over 1 minus x squared. And of course, there are chain rule versions to that, which I wrote down here, and the chain rule version to that, which I wrote down here. So those are just some new formulas. Conceptually, there's nothing else to tell you about that. It's just kind of the same old, same old. I just gave you a new formula to work with. And yeah, all the derivative rules, everything else still applies. Like here, we did the product rule. Chain rule still works as expected, everything, right? It's just that I gave you some new formulas. And you can now go and do what you've always been doing with these new formulas. And here we just reviewed doing implicit differentiation with like a sine inverse here. But again, in principle, nothing really changed. It's just that I now know when I see this guy, the derivative looks like that guy, right? So that's really all that happened. What else did we do? Did one of these examples. If we can talk about the derivative of the inverse at a specific point, and pretty much you can use this formula here. And to find the inverse at a particular point, what you do is you set your function equal to that value, right? Because if your inverse function of some number is some unknown, it means that f of that unknown, the original function applied to that unknown, is what gave you that value. You can then get an equation which you can solve by inspection. And in this one, you didn't really have to solve by inspection, but there are a lot of examples where you do, where you're deliberately given, this equation is deliberately one which they know you can't solve other than just by eyeballing it. And the fancy way of saying that is by inspection, because saying we guessed it or we eyeballed it doesn't sound as professional. So we said by inspection. We can see clearly, right? You have to throw in the word clearly there as well, so that if there are people in the room who didn't see it, they're like, wow, this dude is on another level. He's like, it's clear to him, it wasn't clear to me. You have to do that. It's required. So you say, well, obviously, clearly, x equals 1 is the solution. So yeah, you can do that. And you say, by inspection, clearly we can see. And then you just plug it into the formula. Again, nothing too crazy. I then started writing in a much bigger font for no reason at all, moving on to linear approximation. Maybe that's because this is one of the most important applications of derivatives, even though technically we only did some very simple, simplistic problems with it. It is a very important property. The idea is to approximate what the output of a function is going to be by essentially telling yourself it's going to be roughly what the output of the tangent line at that point is going to be. And this works pretty good when you're very close to the original point. How good? A lot of systems in the real world are built on this assumption. And yeah, your GPS takes you where you're actually supposed to go, all that sort of thing. It works, right? So we kind of know it works. So at least on the scale that we're using it. So yeah, and we did an example of that, which this is pretty much the kind of example I would ask you about if testing this kind of problem, is to just give you some weird number to compute by hand. And again, it's a matter of plugging into the formula. X is the value that you don't know. It's kind of like the guy you want to approximate f of x for. But A is a nice value that's close to x for which you know the value of f of x for. So in this case here, we wanted to approximate the square root of 3.99. The function square root of x seems very appropriate. Our x, the ugly value that we really don't know any information about, is 3.99, while A is 4. It's a value super close to x for which we know the values for, because radical x as well as 1 over 2 radical x, it's very easy to compute that at the value 4. And so we can use those values to approximate, and we got it within 4 decimal places in one situation and within 6 decimal places in the second situation, which is just really dependent on the function, actually. If your function grows very slowly in relation, you'll tend to be more accurate because your function actually doesn't change much. Whereas if your function grows quickly, your approximation tends to be off a lot sooner. Linearization, that's a formula, again, sort of plug and chug. Differentials, it's essentially the same as linear approximation, except pretty much it's a notation change. Instead of the f prime of x times x minus f prime of a times x minus a, you have dy in that position. But the idea is, in some situations, you can have a formula, and based on small changes in the variables, you can figure out small changes in the original function. And we looked at that. Then we went into more facts about the derivative because I do want to get into some applications, which I think finally we're going to get into today. But I do need you to know some background about derivatives. We spoke about the fact that we can interpret derivative as the slope of a function. And because we know about slopes of a straight line, if you're moving up from left to right, your slope is positive. If you're moving horizontally, your slope is 0. If you're moving down as you go from left to right, your slope is negative. And if you're moving straight up vertically, your slope is undefined. That kind of tells you that since the derivative is a synonym for slope, it literally means slope. It just means it in a more general context than we're used to, because before we only knew about slope for straight lines, but now we know about slopes for anything that looks like a straight line when you zoom in. So we know that the derivative would behave in the same way. So when our derivative outputs a positive number, it means the function is increasing. In other words, it's going up as you go from left to right. As x increases, your output will increase. And we know that if our derivative is negative, it means decreasing. We then looked at higher derivatives. The idea is sometimes you can take derivatives repeatedly. So you can have a function, you take a derivative, and then of that result, you can take another derivative. This derivative is called the second derivative of the original. Then you can take a third derivative, a fourth derivative, fifth derivative. Not always, but there are a lot of functions which you can do it. And pretty much every function you'd see in Calc 1 is a function on which you can do this. So we looked at the notation for that, and we looked at one of them specifically. We singled out the second derivative. It is the other one that we're going to use a lot of information for. One application is to the physics of motion. Acceleration can be thought of as the second derivative of position, as well as concavity. And concavity is where we kind of wrap things up. It's talking about the shape of a graph. Essentially, we are concave up. in a region where a second derivative is positive on that region, and we're concave down on a region if our second derivative is negative on that region. And pretty much this talks about the shape: concave up like a cup, concave down like a frown. It's talking about whether you shade like a smiley face or a frowny face. It's talking about how you're curved, essentially. And it doesn't matter if you're increasing or decreasing. Concave up or concave down has nothing to do with that. It has to do with the shape of the graph. So yeah, the first derivative is what tells you about, is it moving up or down? Concavity, or concave up versus concave down, tells you how it's shaped while it's moving up or down. And we're going to talk about the significance of that in a little bit. But now, the next thing I wanted to go into was the idea of an inflection point. So let's do that. This is not. So let's talk about points of inflection. Yes. AKA inflection points. Okay, so what is a point of inflection or an inflection point? This is pretty much a point where you switch concavity. So before that point, you were concave down. Then after that point, you're concave up. And your function actually passes through that point. So it's a point where your function is continuous at that point, and at the same time, you switch concavity on either side of that point. This point is called a point of inflection. So it can go from concave down into concave up, or concave up into concave down. So let's talk about that. An inflection point, let's say, of a function. And F changes concavity on either side. Point. So an inflection point would look something like that, or something like that, or something like that, or something like that. So if blue dot equal point of inflection, then here it's probably around like here, give or take. It's probably around like here, give or take. Right. So you'll see that on this side, if I were to look to the left, I am concave down. Whereas if I were to look to the right, I am concave up. Right? So on the left, I'm down like a frown. On the right, I'm up like a cup. And I switched that behavior once I passed through this blue point. So over here, we realize that our f double prime was less than 0. And then immediately on the other side, my f double prime is greater than 0. right? So that's a point of inflection. And this can happen in various ways, as you can see here, 4 different examples. These guys over here, our function is increasing, f increasing, which means that our first derivative is positive for both of them. And over here, f decreasing, which means our first derivative is negative for both of them. And so increasing, moving up from left to right, means your first derivative is positive, and decreasing, moving down as you go from left to right, means your first derivative is negative. However, your second derivative tells a different story. Your second derivative can switch values during this time. And your second derivative really tells you about shape. So if your second derivative is positive, concave up like a cup, shaped like a smiley face. Second derivative is negative, concave down like a frown, shaped like a frowny face. And let's deal with the ever important question, like why is this important? Why do we care? So when you're doing something like this, versus something like this, notice that this all doesn't just tell you about what increasing. They're both increasing, right? So this one, this is increasing and that is increasing. However, what you'll notice is that this one is increasing at a slower rate over time, right? So it increases by a lot in the beginning, and then it increases by a little bit here. So if we were to plot this over here, like the y-axis, you realize that in a very short period of time here, the increase is much larger. And in the same window of time over here, the increase would be much smaller. So you can actually plot that right beside. You can actually imagine that there's a y-axis over there measuring how high you're going. And this one over time will go higher by less within the same time period. In other words, this one is increasing, but increasing at a decreasing rate. Right? So that's increasing by less over time. Right? Same thing here. Well, a similar thing here. This is increasing, but increasing at an increasing rate. Right? So that's increasing by more over time. Right? So it's not just like, oh, my graph is shaped like a smiley face or a frowny face, whoop-de-doo. No, it actually means something. It means whatever behavior is going on, it's either accelerating or it's decelerating, right? It's actually happening faster and more, or it's happening slower and less, right? So the same behavior is occurring, but there's a change in how that behavior is occurring. It's kind of like I'm driving a car moving forward. I'm going at the speed limit, right? So because I'm very responsible, which is like in the city's like 25 miles per hour. So I'm moving forward at 25 miles per hour, but then I take my foot off the gas. I would still be moving forward, but I would be moving forward slower and slower. So if you were to track me just moving forward in a car where at the beginning I was moving at 25 miles per hour, but then I take my foot off the accelerator and now the car is just running, this would be the picture that would describe that, right? As opposed to the opposite. If I was moving forward and I put my foot on the gas and started accelerating and I started going faster, this would be a picture that would describe the car. And so you can tell that these two things, they actually mean a lot different. So in theory, overall, the same behavior is happening, but the way it's happening is different. And that can tell you a lot, right? And so it's kind of like, that can make a world of difference. So it's kind of like one example is, just to be controversial, because that's what we do here. You talk about global warming, right? And some people believe in it and some people don't. And one argument is, well, the Earth has always been heating up. And the idea is, well, yeah, the people who think global warming is a problem it's not that they don't believe the Earth was always warming up. They're just like, no, it's just warming up at a much faster rate than it used to be, like many times over, right? So the thing is, it's not just a matter of doing this, it's a matter of doing this. And that can mean have a lot of consequences on life, on ecosystems, on, composition of the planet, as far as icebergs go and all that sort of stuff. So it matters how things are changing. So it's not all the time good enough to just know, oh, it's getting more or it's getting less. Sometimes you want to know, well, how is it getting more? How is it getting less? Is it getting more by more, or is it getting more by less, right? That actually can matter a lot. And similarly, if I have something decreasing like this, or versus decreasing like this says decreasing, but at an increasing rate. So it's decreasing faster and faster over time. And this one is decreasing, but at a decreasing rate. And you have to remember what mathematics helps us with. It's to model things. For people who actually care about using math in real life, math is a model. So it's not always just about, oh, I can draw this pretty graph and this is just a random f of x. In real life, your f of x is going to represent something. So if you think about interpret the following curves under the context given for f of x, what you'd realize is that, all right, if I'm looking at this versus this versus this, that was super vertical. That's not great. Versus this versus this, right? So, and in one hand, you're like, let's do in blue, f of x equals, so here's one interpretation. F of x equals our profit on day x, right? Now, if you look at this function as graphing your profits, now you'd realize that in that case, these two guys are good, right? We can even get more specific, and that's the point. So the first derivative would tell us that those two are good, but the second derivative would tell us even more information, right? So this one here, they're both good. But you see, this one over here is better, right? So here's what f prime can tell us, and here's what f double prime can tell us, right? And so that's one interpretation, okay? And over here, this would be, they're both bad. But if you were in one versus the other, it would actually be better to be over here. So the first derivative can tell us that it's bad. The second derivative tells us how bad. Is there hope? And so what you can realize, I'm going to need one more space here. What you can realize is in the first situation, in the far left, profits are increasing, right? So yeah, that's good. However, in the beginning, like over here, profits were increasing, but they were increasing at a decreasing rate. So it's like, yeah, we're making money, but things are kind of slowing down. We made less money this week than we did last week. We're still ahead, but something might be on the horizon. And then some point happens, boom, and then suddenly, whoa, business picks up. You're now increasing, you're getting larger and larger profits, but much faster. So if you were the owner of this business, you'd probably want to know what happened here. Maybe we should do more of that. You'd want to identify that point. How would you identify it? You can't with the first derivative. You can with the second. And so that would be good. As opposed to this one, hey, business is good. It's great. We're increasing in profits and we're increasing more and more over time. Then something happens and yeah, business is still good, but it's kind of slowing down. I don't know what happened right here. I want to know what happened right there, right? As opposed to over here, you're like, well, things are bad. We're bleeding money. It's horrible. However, something happened. Things are still bad. We're not out of the red yet, but things kind of aren't as bad as they were. So maybe whatever happened at some point, we should kind of figure out what happened and do more of that. Or here, yeah, it's bad, but it's not, it's okay. As opposed to after this point, whoa, now we're actually in trouble. Like if we don't figure out what's going on, it's not going to be pretty, right? So your first derivative can tell you about some interpretation, about some of the interpretations, but to get a more accurate interpretation, to really understand what is going on, you need the second derivative. Now, if you go and you say, I don't know if pink, if now you change the interpretation of your function, it's not just some random f of x, it's actually a function that you care about, right? Like the blue function someone would care about if they own the business, right? And they would want to know what's going on with their business. So what if this was the size of a malignant tumor? Now, all right, so you're watching the size of your tumor on a graph. That function is now important to you. How much information would you want to know about such a function? You'd want to know everything you can possibly know about that function. And now this interpretation completely flips. You see this is now bad, right? You don't want that tumor to be in growing, right? You kind of want it to be getting smaller by whatever medication or whatever protocol you're on. However, this part here is worse, right? If your tumor is growing, you'd probably want to be in the second situation as opposed to the first. Over here again, this is now good, right? Interpretation completely changes, but now you can also know which one you would want. Over here would be worse, right? So you can flip the interpretations, and the thing is, the only way you would know about if it's getting worse or better is the second derivative. The first derivative just gives you this bird's eye view, this overview of what's going on. All right, we're increasing, we're decreasing, we're moving up, we're moving down. But the second derivative can give you a lot more tailored information. So I just want to mention that because a lot of things get lost in Calculus 1 when you're just learn to solve this problem and you just move on and you never really know why it's meaningful. Thought I'll just say that because a lot of people just never get to that point. You're like, I learned all this math in school, never used it. Well, I mean, I don't think you fully understood what was going on because if you did math in school, you'll definitely use it in the 21st century. Like reading information on the internet and interpreting information is, if you're better at math, you can do it better. Like all else being equal, the person better at math can interpret information better than the person who isn't. So it's not that you have to be doing all this technical analysis all the time. It's very important that you understand like what this all means. What does it all tell you? What does it all mean, Basil? Right? So for you guys, I'm going to test your knowledge on this by just having you draw pictures of graphs, which, okay, like no one's ever going to do that. I get it. But it's more important that you understand what does that shape that you just drew means and what interpretation could you put on it if you actually cared about that function you were graphing, like it was actually something important to you. What would it mean that it's shaped this way, right? So yeah, so it's pretty important. So there are some tests that we can use to identify these things. So let's talk about that. To examine where the above behaviors take place, right? So we'll cover two. So as I mentioned, knowing this property is going to be important. So for example, finding this coordinate right here is going to be very important. So knowing that something good happened or something bad happened at some point is sometimes not good enough. You actually want to know, well, what was that point? What was going on, right? If our profit suddenly started not doing as well, like when did it start to not do well? What was going on? Maybe a competitor opened a store across the street. Maybe if it started going better, we started a new ad campaign. And you're right, so you want to know when the thing happened. So there are some tests that we can do for that, where we can't just know, it's increasing or it's increasing at an increasing rate starting at this point. We can actually find the point. So these are one, it's called the first derivative test. And two, it's called the concavity test. And these are used for different purposes. Maybe I should mention it here. So the first derivative test, as we mentioned earlier in class a couple of days ago, this can identify when your function is increasing and decreasing. It turns out being able to do that, you can also identify some other things like maximums and minimums. We'll get back to that. For now, you can have an intuitive, I think you have an intuitive interpretation of what that means. So this is used to find where our function is increasing or decreasing. And as a bonus, also finds maximums and minimums. And yeah, that's the first derivative test. The first derivative test helps us find all that stuff. The concavity test used to find concavity. I mean, if it didn't already said that, used to find the concavity. Kind of state it in the other way. Used to find where f of x is concave up versus concave down. And it also finds inflection points. There is a third test that's pretty popular. It's taught usually in a Calc 1 class called the second derivative test. And for us, we're kind of going to ignore this because the first derivative test will give us all the information that we would need to know that the second derivative test would give us. The second derivative test is kind of a way to use the second derivative to tell you about maximums and minimums. Find, not all of them, find some maxes and mins. So on one hand, it's not as far reaching as the first derivative test. You can use the first derivative test to essentially find any maximum or minimum. The second derivative test can only identify some of them. Your second derivative has to be well behaved at that point. And the first derivative test can tell you all of that and more. So in one situation, I'm literally always going to have you, in any situation where you would need one of these tests, you're going to have to do the first derivative test anyway, which means the second derivative test is now superfluous, it's useless. And even if you didn't want to do the first derivative test in the first place, the second derivative test gives you less information. So if you just want less information and you want to do something quickly, like maybe you're writing a computer program or something, you can just ask the computer, oh, do the second derivative test for this one thing. But the first derivative test is far more general. And so it covers everything the second derivative test would cover and more. So I'm essentially just going to ignore this. If you ever need it, it's not going to be something that's difficult to understand. Like you'll read the statement, and you'll know, oh, it's basically what it says is that where the second, if your first derivative is 0 and your second derivative is positive, remember second derivative positive means concave up. It means that you'd have a minimum at this point, versus if your second derivative is positive, is negative, you'd have a maximum at that point. That's essentially what it tells you. But your derivative has to be well behaved there. So if your derivative does not exist, you can run into issues. You can't really use this test. Whereas the first derivative test, you can use it even if your derivative doesn't exist. So it's a pretty comprehensive test, and it covers everything and more that the second derivative test does. So I'm kind of going to just have you guys focus on the first derivative test, actually. And yeah, skipping the second derivative test. So yeah, so let's actually do one by one. One. Okay, so this is a test you're going to want to know very well, because there's going to come a point where I'm going to give you certain problems where you have to do a bunch of tests, the first derivative test and the concavity test being one of several, and you kind of have to do it all in the same problem. So you don't want to kind of be shaky on the first derivative test, because then that problem, which is already going to be long, is going to take even longer. You're going to want to know, oh, the first derivative test means this, I can just do it, follow my nose and get through it, right? So let's get through it. So we want to find behaviors like, I mentioned this already. Find where f is increasing, decreasing, and where f has maximums or minimums. So remember what that means. It's like your function is either you want to identify if it's moving up, if it's moving down, or you want to identify when it does something like this, or it does something like that, or it does something like this, or it does something like that. And I drew some sharp corners on purpose because I do want you to understand that we can still use this even where the derivative is undefined. And we know from earlier that the derivative is undefined at sharp corners. So this is, function is increasing, going up. Function is decreasing. Here's an example of what a maximum would look like. And here are some examples of what minimums would look like. Right? So max is like the highest point in some region, and the min is like the lowest point in some region. Turns out you can use the first derivative test to identify all of these behaviors. And I'm essentially going to tell you about the test in terms of how you would actually go about doing it. So step one. So it's called the first derivative test. So you would think that you would need to find the first derivative at some point in the test, and you do. It's the first thing you would find. So you would first find f prime of x and all critical points of f. Now, a critical point, I am going to be identifying some of what I'm talking about here in detail later, but this is just where f prime equals 0 or undefined. And I'm going to explain why we want that particular condition, but that's what a critical point is. So that's the first step. Find the derivative, find all the critical points. The second step, plot the critical points. On a, say, number line. There are various ways to actually do this, but I think this is the nicest way. Right. So let's talk about what we can expect, right? So, or what it would look like. So here's a number line. And then I would have here, let's say that's where my critical point is. X is a critical point. So that's a point where if I plug it into the first derivative, I would either get the answer 0 or I would get the answer does not exist. It actually doesn't make sense, right? And so you're going to plot the critical points on a number line, and you're going to, and you may have several, right? May have several. Right, so that could be 1, this could be 1, that could be 1, etc. Right, so that's what you're going to do. Now, step 3, here's where the actual test is going to come in. Now, you can do all this at once, but I'm really breaking down the steps. I'm going to go through some examples at some point later where you're going to see me do this all at once, but I'm kind of just, I want to show you like what you should think about first, second, third. I'm just kind of dissecting the thoughts here. So you don't have to actually know each of these steps individually. You should kind of just know how to go through this whole process, like in one fluid motion. So you're going to pick random points, and it can be completely random, in between all critical points. Right? So you're going to pick some random point. So you're going to have, here's your critical point, X, critical point. And you're going to pick some other X, like X1, random X value. That is smaller. And here, say X2, you pick some random X value. That is larger. Right? Now, it doesn't matter who you pick as long as you're not on top of a critical point and as long as you're in between all the critical points. But of course, in general, you're going to pick a nice number, right? So you wouldn't just pick some random decimal expansion. You might pick a whole number that you can do calculations with easy, but it doesn't actually matter the specific number. So you're going to pick some random numbers. Now, step 4, you're going to test these numbers. You're going to test each of these random numbers. And by test, here's what I mean, i.e., plug each into the first derivative. And compute their sign. Now, I'm going to emphasize sign here because we don't care about the specific value. Like once you could identify whether the derivative is going to be positive or negative, that is good enough. You don't really need to know the specific value at all. So yeah, and step 5, conclude based on the following. Okay, so once you do this, you can end up in a bunch of situations. Okay, 2 of them are very special, and then everything else you just kind of categorize as, well, nothing of interest at this point is going on. So here's one situation. What you can do is you can have the critical point here, and over here, you have your x1, you have your x f prime. When you plug in x1, you get something greater than 0. And when you pick the random value over here, f prime of x2, you get something that's less than 0. Now, what that means is on this side of the critical point, you're going up as you move from left to right. And what that means is on this side of the critical point, you're going down as you move from left to right. And at the critical point, your derivative is 0 undefined, so it's not going up or down, right? So that kind of tells you, as long as this point is in your graph, like it's not a hole or it's not like an asymptote or something, as long as it's on your graph, what you've just identified was the maximum point. You are rising before that, and then you fall after that, which means at that point is where you were the highest you've ever been, right? So you can actually identify the maximum by just knowing the increasing and decreasing behavior. So now, if f is continuous at x, maybe I should. So here's a case 1. This happens and this happens. If f is continuous at x, then f has a, it's called local maximum at x. And it's very important that you check that it is continuous. So the point has to be there because it's possible for this behavior to happen and there's a hole or an asymptote, right? Think of like 1 over x as x at x equals 0. Like you're increasing on the left and you're decreasing on the right, but you do not have a maximum at 0, right? Because there is no point at 0. So your function has to be continuous there, which we now know how to check for continuity. So once your function is continuous and this behavior happens, it means you have a maximum. Right? The other case is, as you can guess, the case where you can identify minimums. So we have our critical point right here. And over here, x1, x2, pick some random values. I'm immediately going to plug them into the first derivative. What if I got a negative here and I got a positive here? Then it means over here I'm decreasing and over here I'm increasing. And if we're continuous, what it means is that I've just identified a point on the graph where I am falling before that point and then rising after that point, which means that point has to be the point where I was the lowest I've ever been in that region. So if f is continuous at, so word at, that's not much better, at x, then f has a local minimum at x. Okay. So here's how you can, one, you can know where it's increasing and decreasing because the sign of the first derivative tells you that. And two, if you see a particular behavior, you can know where there's a maximum or a minimum. And okay, case 3 is pretty much any other situation. And in any other situation, so this means like you have like down, down, or you have like up, up maybe, or something like that. Then we cannot conclude max or min from this test. But we can still tell increasing, decreasing. Right, so that's how we can identify maximums and minimums, and where we're increasing and decreasing with the first derivative test. That is, that's the first derivative test. So you have a function, and really, I'm writing out a lot here, but that's just me trying to explain it to you. But this should all happen, hopefully, relatively quickly. Like you should be able to. It shouldn't be something that takes you long, and you should really only be drawing one number line, and you do everything on that one number line. You do it all at once. So first thing is you find your critical points, you immediately draw your number line, plot it, you'd write two numbers on either side, two random values, you plug it in your first derivative and check the sign. If it's positive, it's going up. If it's negative, it's going down. And if you notice the arrows behave in a certain way and your function is continuous at the critical point, then you can identify maximums and minimums. Otherwise, you can't. So that's pretty much it. The concavity test is actually pretty similar, but of course it talks about concavity, which means we're essentially going to do the same thing, but with the second derivative. So here, sometimes just to remind myself, I will literally write f prime beside the number line to just remind myself, plug into f prime, plug into f prime, plug into f prime. So I would literally just write f prime here. Right? And the concavity test is pretty similar, except you use the second derivative, and this time the positive and negative tells you something else, right? So 2, the concavity test. Okay, so this test, find where f is concave up, concave down, and where f has inflection points, if any. Or I say that here, like your function doesn't have to have a maximum limit. Okay, so this one can identify several things. So it can identify when your function looks like a frowny face, when it looks like a smiley face, or where any of these behaviors that we spoke about last time happens. I just use the same thing. I totally yeah, so like it identifies these points and it identifies this behavior. So it identifies concave down or concave up. And all of these are just like various inflection points. So you want to find where those points occur, where we switch concavity. So I want the format to look a bit different. Right after that, I said step 1. Okay, so step 1, you're going to find f double prime. And the critical points of f prime, i.e., where this second derivative equals 0 or undefined. I want to say I put that in blue last time. Okay, so you're going to find the second derivative. You're going to find the critical points of the second derivative. So you're going to plug in, find where the second derivative is 0 or undefined. Obviously, that's going to be algebra. And then step 2 is to plot the critical points on a number line. So boom, boom, boom. Put the second derivative here. X is going to be a critical point. And course, maybe several critical points. And I feel like doing this. Okay, yeah. So first derivative test. Okay, here. Pick a random value. That's going to say test all random values. Plug into the second derivative. And compute the sign based on the following. Yeah. Yeah, so it's actually very similar, as you can tell, to the first derivative test, but you're just using the second derivative and it means something else. So pick a random number in between, test the random numbers, plug into the second derivative, compute the sign, conclude based on the following. If the second derivative is positive, that means concave up. Second derivative is negative, that means concave down. And if f is continuous at x, then f has an inflection point. In the second situation, your second derivative is negative. That means you're concave down like a frown. Second derivative is positive, means you're concave up like a cup. And if your function is continuous there, then f has an inflection point at x. And if you're in any other situation, like, here was the critical point and you're like concave up and concave up, you actually don't switch, or concave down, then we cannot conclude inflection points. Inflection points. But we can still tell concavity. Yeah, so that's the first derivative test and the concavity test. So maybe I should kind of do a summary here. So here's something I want you to take away from this, which we're going to come back to later. What I want to do for the next topic would actually only require you to know that increasing means derivative is positive and decreasing means derivative is negative. But later on, we're going to be using the information that I'm giving you now. So you might as well start thinking about it and just kind of assimilating it. And let me just do a summary for you here. Functions and their meanings. So here's the function, which this is going to be, I think, a long table. Maybe. It's totally not straight. Okay, so I'm going to tell you about the different type of functions. I'm also going to tell you about what it tells us. And then I'm going to tell you about how it tells us. So let's deal with everyone's favorite function before this, f of x, right? So this is the original function. Now, when would you use the original function? What information can you get from that function? So it can tell you about points on the graph. It can tell you about position, location, current state. Right? So stuff like that. Like, where are we now? What is our current state? What is our current location? What is the coordinate on this graph? Right? You want to answer questions like that? This is how you do it. And basically you evaluate. Plug in the x, compute y. To get the coordinate x comma y. And so that would tell you at time xy, that's a position or location or whatever. Okay, so that's pretty much, yeah, that's algebra, pre-calc, right? So that's nothing different there, nothing new there really. So that's what the first kind of function can tell you. However, we can take derivatives now. So another kind of function is y prime equals, or let me write the Leibniz version, or something like dy dx. This is f prime of x. What can the derivative tell you about? Well, it tells you about increasing, decreasing. It can tell you about maximums and minimums. Right, so from the first derivative, this is the information you can get. You can get when the function is increasing, when is it decreasing, when it does it hit a maximum, when does it hit a minimum. These are things that you can tell using the first derivative. How would the first derivative tell you this information? Well, I just explained it to you, the first derivative test. guess this table is not going to be that long because I summarize. Usually I kind of like write the whole first order test in like this little cell right here. But yeah, I've decided to do it separately. Yeah, so that's what I can tell you. The second derivative. So obviously this is d squared y dx squared. This is f double prime. What can this tell you about where a function is concave up, concave down, inflections? How does it tell you? The concavity test. Okay, so that's a summary. And this is just stuff we know now. Like this is what each function, based on what kind of information you want, you would use a different kind of function to get that information. So you want to know about current state, current position, where are you, plot a coordinate on a graph, use the original given function. You want to know, is this function increasing or decreasing? Where are the maximums? Where are the minimums? You're going to want to use a first derivative, at least in Calc 1, right? Because we're doing calculus. If you want to know about concavity, where is it concave up or concave down? Where is it shaped like a smiley face or shaped like a frowny face? Where are inflection points? Where can I identify where it's increasing, but it starts increasing at an increasing rate versus a decreasing rate? Things like that. So yeah. And again, recall derivatives may not exist, but the concept of critical points covers this case. Right, so derivatives are limits, they might not exist, but yeah, critical points take care of that. But it's very important that you know what each function is and what it's good for. What is it good for? Okay, so is there any other information dump I want to give you? Not really. I think right now we can go into should I do maximum browser applications? I mean, I want to go into applications. We spent a while just doing information dump. I kind of want to like do some problems. So next we'll do some applications. And it's kind of a natural place to break here. So I'm going to break. I'm gonna take a break now, and we'll come back around 7:30ish. Yeah, seems like a good place to take a break. So yeah, I'll see you guys back here around 7:30.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
Okay, we are back. And we're going to start a new topic, related rates, which I already wrote up the notes for. This is the section where we're going to solve certain word problems. So they're called applications. And I decided, well, I don't want to write out all these word problems, so I'll just type them up. And I was like, well, since I'm typing up stuff anyway, might as well type up the notes. So that's what I did. We're just going to walk through these and then get to this problem type, do a bunch of examples, make sure that we get used to it. On one hand, these problem types are I guess, longer than usually the problems that you will be doing are. Not the longest, but they're longer type problems. You'd have to, of course, read and understand the information, and then there's the whole writing out the solution. But the saving grace is it's pretty much the same sequence of steps to solve any of these problems. And so once you really understand those steps, the problems shouldn't be too difficult. So let's actually get into it. So the idea is the following. When you have two quantities are related, right? And related in the mathematical sense means that there's a relationship that we can describe that connects two quantities, right? So usually that means an equation. Not always, but usually, right? So if I say, oh, there's a relationship between x and y, it means I have an equation that connects x and y. Y equals x squared. That's a relationship between x and y. And we can say x and y are related. Whatever x is, y is going to be the square of that. So that's the relationship that they share. So the idea is there are times when I'm interested in finding out the rate of change of something. Obviously, that's what solving the rate problems means, but I can't get a handle on that thing directly. However, I know how to find the rates of change of something that's related to that thing, right? So I can find the rate of change by using related rates, right? So the idea is if quantities are related, then their rates of change are automatically related, right? So if I have a relationship between x and y, then I automatically know the relationship between the derivative of x, the derivative of y, right? Because I can just differentiate the whole equation. So once I have a relationship, I can turn that into a derivative relationship by just differentiating the original relationship. And so that's where the name related rates comes from. So we are going to use related rates to figure out the rates of change of things that we care about. So that's the basic idea. So because there are going to be several types of word problems moving forward, I do want you to be able to identify when you're looking at a related rates word problem versus some other kind of word problem. And here is that section. How do you know you're looking at a related rates problem, right? So test 2 is going to have several word problems on it. How do you know which of them is related rates? Well, they have a very nice format. So one, they're going to describe to you some related quantities, right? And not always, but many times it's going to be a geometric relationship, for example. So they can talk about, oh, the length and width of a rectangle, or the height and base of a triangle, or, oh, this field over here has the shape of a triangle and length is changing, whatever, right? So they're going to tell you about some related quantities. And then what they're going to do is they're going to tell you the rates of change for some of the quantities, but not all of them. So they're going to say, oh, the length and width of a rectangle, the length is increasing by this much and the width is decreasing by that much. How much is the area? What is the rate of change of the area, right, at a certain point, right? So that's how the questions are going to be phrased. So they're going to tell you about related quantities. They're going to give you the rates of change of some of them, and they're going to ask you about the rates of change of others. And so you're going to use these related rates to figure out the rate of change of the unknown quantity, the unknown rate of change that you care about. That's basically the idea. So any word problem that kind of has those elements to it, it's a related rates problem, right? Here are some quantities that have relationships. Here are the derivatives of some of them, the rates of change of some of them. What is the rate of change of this guy? That is a classic related rates problem. Now, once you know that you're looking at a related rates problem, what do you do then? Well, it turns out you do these 6 steps. Always these 6 steps, always in this order. So I now know, all right, I'm looking at a word problem and it's definitely a related rates word problem because, I know what to look for. So now that I know what to look for, what do I do? So step one is kind of the step you should have done already. Read the problem carefully. It's going to be very important that you read carefully because there are going to be nuances to each problem that you have to pick up on. Also, you have to read the problem to even know that it's a related rates problem in the first place. So you have to read carefully for that. But there are going to be situations in which you really have to worry about how things are changing. So like we were discussing earlier, a positive derivative means something is increasing, while a negative derivative means something is decreasing. So if they tell you, oh, this quantity is increasing at this rate versus this quantity is decreasing at this rate, you would need to know that, oh, a positive sign should go on this rate and a negative sign should go on that rate. So you'd have to actually pay attention to the word increasing or decreasing. Or you'd have to pay attention to the situation that they're describing, and then you'd have to realize that, oh, this thing is increasing or decreasing. So whatever change they tell me, it should be positive or negative, right? And so you have to pick up on all these little nuances, right? So reading carefully, very important. Students don't read enough. That happens a lot. Let's not get into it, right? But reading is fundamental. The second one is if possible or necessary, and I'll talk about when it's necessary, but draw a diagram. And you want to label that diagram properly, right? So you are going to label quantities that are changing with variables and any quantity that's not changing with constants, right? So if it's not changing, write down a number. That's it, just write down the number. If it is changing, then you would write down a variable, right? So you'll draw a diagram to describe the situation. They describe a situation, you draw a picture of the situation, if possible, if necessary, and then make sure you label it properly as well. And then what's going to happen is technically that picture will be changing, it will be moving around, and you need to basically know, based on how things are moving, this is increasing or decreasing, and so I should know what sign the derivative should take and whatever. So again, you'd have to read very carefully to be able to do that. Step 3 is a step that is, it's kind of for your benefit. It kind of is you setting the goal of, you know what you want to find. So you're going to write down all the things you know, or write down all the rates you know, and then you're going to write down the rate you want to find and at what point you want to find it. Essentially, that's what step 3 is. So you're just going to say, this is what I know, this is what I want, and now I have a goal. I know at the end of this problem, I should be able to say this. So I think that's always a good thing, so you don't get lost. So step 4 is where you're going to set up an equation. So this equation is going to be the relationship between the variables. Now, if you're given, say, a diagram, so it's a rectangle, and they're telling, oh, the length is changing this much, the width is changing this much, how's the area changing? You automatically have an equation that relates all those variables, right? So you can just create that equation. And the diagram is what's going to help you do that. You can like look at the diagram and see what equation is going to work. So that's what's going to happen. Now, when is a diagram not necessary is specifically when this relationship is already given to you. So if you're in a related rates problem and they told you, oh, here's the equation, then you don't need a diagram. You already have the equation, right? The point of the diagram is to kind of help you set up the equation and to know how things are changing. So if you're already told the equation, you won't need a diagram, chances are. There are some rare cases, and I think we'll actually do one. I think there's an example I plan on doing here where it's like, even though they gave me the relationship, there was some unknown that you can't figure out that the picture would help you to figure it out. Even though technically you could maybe figure it out some other way, the picture would help. So diagrams are helpful either way. Once you have the equation, now you're in business. Now it's calculus. Differentiate that equation. You're going to differentiate it implicitly with respect to time. That's actually an important thing. Your independent variable in these problems, it's always time. With respect to time, t is always going to be your independent variable, which means because we know about implicit differentiation, what that means is anytime we differentiate a variable that is not t, we have to multiply by the prime, including if the other variable is x. Right now, if you see an x, it's a dependent variable. It's just like a y. It's actually a function of t. T is the independent variable. Very important that you know that. So that will tell you how you want to differentiate, because the differentiation is implicit. Okay, so we don't care necessarily about the quantities themselves. We care about how the quantities change in relation to time. Over time, how is it changing? So time is always going to be the independent variable. After that, you're going to get to step 6, which is where you're finally going to wrap things up and solve the problem. You're going to plug in your knowns, solve for the unknown, and there is a hiccup that could happen. There are times when you may have several unknowns. In that case, you should panic. No, you shouldn't panic. In that case, what you want to do is you want to go back to the equation in step 4 and use that equation to figure stuff out, right? So the diagram will help you come up with that equation, and that equation will help you find anything you need to find that wasn't given, okay? And that's basically it. So you're going to read the problem. You're going to draw a diagram. You're going to write down what you want and what you know and what you want. You're going to set up an equation. You're going to differentiate that equation implicitly with respect to time. Then you're going to plug stuff in and solve for the thing you want. Occasionally, you can't do that all in one shot. You're going to have too many unknowns. So what you do is you go back to step 4 and you're like, okay, let me find the extra unknowns that I don't yet know. And then you go back to step 6. And that's basically it. And the idea is you should know this process like by heart. You should just know what you should be doing next, right? And it's pretty much always going to be these steps in this order. And if something isn't relevant, for example, like I said, it's not always important to draw a diagram. You just skip over that step and move to the next step. So like if you're given the equation, just skip over step 4, move to step 5, right? But you want to kind of move in this order. It'll help you find things in the right order that you're going to need. And yeah, so without further ado, well, there's one other thing I want to mention, which I think here. Yeah, geometry is very geometry is very prevalent with these problems. So a lot of the word problems are going to describe some sort of situation, and it's going to be geometric somehow. Like you can draw a picture of it, and it's going to be a geometric shape that you're supposed to be familiar with. So you need to be familiar with your geometry formulas. So how to find the area of stuff, how to find the volume of stuff, how to find perimeter of stuff, that sort of thing. So hopefully your geometry is up to snuff. It doesn't have to be perfect. Like you're not going to need to know the circle theorems or anything like that. But you should know how to find the area of a triangle. You should know Pythagoras' theorem. You should know how to find the area of a rectangle. You should know how to find the volume of a prism, volume of a cylinder, volume of a box, stuff like that. The basic stuff. But you can forget the basics too. So if you've forgotten, you need to review this. It's going to be important. So other than that, there's really nothing to say. Knowing your geometry and then going through these 6 steps will get you through the problem. So are there any questions on the steps so far, or what I said? Because I think when I start to go through some of the problems, you can ask questions then, because you'll see what I'm talking about. So there are some problems here. There are 12 of them. I'm not going to do all of them. I'm going to do a few of them, and you can do the others for practice if you'd like, and which you kind of should. Yeah, so we're going to do some of these problems. So we're going to start with problem 1 and work our way down. I've already decided which problems I want to do. I think I actually snipped them already. So I want to do problems 1, 2, 3, 7, and 9. And you guys can try the rest. And there was another problem I already worked out, but I don't know if I want to go through it. I just, okay. Okay. All right, let's go. All right, here. Examples. Okay, so gonna start off easy. Let's read through this problem. A right circular cylinder undergoes expansion. So we have a cylinder, it's right, it's circular, it's a circular cylinder, and we know it's expanding. Its radius is increasing at a rate of 1 meter per second, and its height is increasing at a rate of 2 meters per second. At what rate is the volume changing when the radius is 1 meter and the height is 3 meters? So reading this, which is step 1, read, we see that it's a related rates problem. How do I know? They told me about some related quantities, the radius and the height of a cylinder. They told us how some of those quantities are changing. The radius is changing by this much, the height is changing by this much. And then what do they ask me? At what rate is the volume changing? They then ask me about some rate that I don't know, right? However, the volume is connected to the radius and the height. So these things all have a relationship to each other. And I know the rates of some of them, but not all of them. So this is a classic related rates problem, right? You see this, and that's related rates, right? It describes some situation where all the things that they talk about, they're related. You know they're related. They tell you how fast some things are changing. They ask you how fast one of the other things are changing. And they give you at a specific point. So because the things are changing, they're not always the same, right? Like at a different point in time, all the answers are going to be different. So they'll tell you the specific point at which they want the answer. And here they told you, we want to know how fast it's changing. At the moment, the radius is 1 and the height is 3. Yeah, so good. 2, diagram. All right, so in this case, we have a right circular cylinder. Now, I don't know if this is going to be much help to us at the moment, because there's nothing about this diagram that you can say, figure out, I think. Right. But maybe actually just drawing this picture will kind of jog something in your memory, brings you back to high school geometry. And like, oh, no, not again, not again, no. Right. And then the formula will pop up in your mind if you didn't review it. That might do something. But a lot of times the diagram can be very helpful, but this is a very straightforward problem. Like the formula isn't going to be there. But you drawing it can also remind you, oh, I can think of a cylinder as a prism, because no matter what level I'm at, it's just a circle. It's always a circle, no matter what level I'm at. So it's the same shape being propagated along some length. I know how to find the volume of such a thing. The volume of such a thing is the area of the base times the height. So that would actually get you the relationship. Once you actually draw it and realize, oh yeah, it's the same shape running along some axis. The volume is going to be the area of the base times the height. And here, I'm just going to say V is my volume. So you can't actually see volume on the picture, but I'm just going to identify it by some variable. That's my diagram. Notice that both the height and the radius are changing, so I label them with variables. R is the radius, H is the height, if it wasn't obvious before. Okay, so that's step 2. Step 3, I'm going to write down what do I know and what do I want. Okay, so what do we know? What are the rates that we know? Well, we know how the radius is changing. So we know what's called dr dt. Now, in this case, I would recommend, you don't have to. So technically you can write r prime and h prime, but I would actually emphasize writing dr dt, dh dt, because I want you to always have it in your mind that t is the independent variable. Usually up until this point in your lives, even for the first half of this class, x was your independent variable. So you kind of want to break yourself out of that and keep writing down t so you know, okay, t is the independent variable. What were you told about the radius? Well, we were told that the radius is increasing at 1 and the height is increasing at 2. And because they were increasing, that is what tells you that this should be a plus and a plus since increasing. And I know to do that because I read the problem carefully. So reading is fundamental. So these are the rates I know. Now, what is it that I want? Well, the last part of the sentence tells you what it is you want. You want the rate of change of volume when the radius is 1 and the height is 3. So what do we want? dv dt. When do we want it? Now. No, we want it when r equals 1 and h equals 3. Okay, so you know at the end of the day, you want to know what is dv dt when r equals 1 and h equals 3. So you have that in your mind. We're going to manifest it. I'm kidding. We're going to calculate it. So 4, here's where you come up with the equation. You're going to find the relationship. Now, hopefully this diagram sparks something in your mind and you remember, oh, area base times height. So that tells you that volume is equal to pi r squared h. And now, and that's it. That's pretty much it. That's step 4. 5, we're going to differentiate. Implicitly with respect to time. Okay, so mini test here before an actual test. How would this look if I differentiate implicitly with respect to time? Someone tell me here, if I go through and I differentiate this with respect to time, what would it look like? Go, anyone. Come on, take a guess. Don't be shy. Need to know you guys are still alive. Any ideas? Alphon, you have an idea?
Professor, the problem is like I can't quite think what like implicit differentiation is at the moment. But
okay,
my guess is that we would somehow have to bring in t into this because like in the formula there's like no t, but since t is like the independent variable, so I'm not really sure.
So what do you remember about implicit differentiation?
I remember that it was like dy dx, and
right? But when does that occur? When do you write dy?
When you have two variables.
Mm-hmm. And when would you write dy dx?
If you're trying to just differentiate, maybe.
So let's say here x squared y plus 3 x squared y cubed. I don't know why I should have just put 3x squared y cubed plus ln of y equals 7x. Like if you wanted to differentiate that, how would you do it?
I mean, do I have to differentiate for all variables or just?
Well, if I were to say find y prime, which is dy, I don't know what. Nice. If I were to ask you to find y prime, which is dy dx. How would that be done?
Well, I could use the power rule, and like the ln y would be just 1 over y, and the power would be like 6x times, but since it's like two different functions, so we would have to maybe use the product rule for the first one.
Right, so this is product rule, and how do we do that?
So it's like f prime times, so the f prime times g plus g prime times f.
Okay, and what do we get here?
So 6x times y cubed plus 3x squared times 3y squared.
Okay, and then what?
And then it's plus 1 over y
Okay,
equals 7.
so where's your y prime?
Maybe we could bring all the y to one side and like solve for y.
Yeah, but I mean, you want to find y prime. You don't want to find y. Where's your y prime go? How would you even get y prime?
Is 7 the y prime? Doesn't seem like it.
If 7 should be a y prime, no.
Hmm.
So that's the important, you want to know when, so that's what I mean. When do you put the y prime? Like you need to know that.
So like you're not trying to differentiate everything, you just try to find like for one variable, because like here we like,
Yeah, I want to find dy dx, but how would I get that? So remember what this means is that you're thinking of your y as a function of x, right?
yeah,
So in other words, if you have y cubed, it's that function cubed, which means if you wanted to differentiate that, what would happen? Well, you'd have to apply the chain rule, right?
yeah,
So you'd have 3 comes down, and then you multiply by a derivative of the inside, right?
right.
So it's like if you were to differentiate this, looking at it in terms of y's, you would have 3y squared you would have 3y squared times y prime, right? So in other words, you would put the y prime every time you differentiated a y, right? So there would be a y prime attached here, a y prime attached here, right? Because over here we differentiated the x, so you don't do anything. Over here is where we differentiated the y, and over here we differentiated a y. But the y is like an inside function, right? So every time you differentiate a dependent variable, you have to multiply by the prime. That's implicit differentiation. Like that thought, like you memorize that thought, you know implicit differentiation. Assuming you know regular differentiation, then just that additional sentence, you now know implicit differentiation. Every time I differentiate an independent variable, multiply by prime, right? So what if I had said something like, let's do this same guy, but now suppose your x is a function of time and your y is a function of time, and I ask you to find, say, dy dt, right? So now your x itself is also a dependent variable. And the t is your independent. Right, so up here, remember, your x was the independent. So when I differentiated the x term, what happens? Like I didn't do anything extra. I just applied the derivative rule and not do anything. But if I differentiate a y term, I have to multiply by y prime because that guy is dependent. And there's an inside function there. So he needs the prime. So if I pretended both x and y were dependent, how would you change it here? Like if I go through and you take derivatives, what would you do now?
Do you just put the t prime to all of them?
What would you write down?
Well, it's like the last one. It's like
Yeah.
6x times y cubed plus 3x squared times 3y squared plus 1 over y equals 7.
Okay, but where are your primes?
Do you have a prime for every one of them? Because like both of them are
T is the independent variable, which means T is the only guy you would not put a prime. That's what that means.
I see.
Anyone who is not T needs a prime. Same thing here. If I have dy dx, it means if you're not x, you need a prime. Every time you differentiate, multiply by prime, because chain rule, basically. That's why you do it, because of the chain rule. But you should know with implicit differentiation, if you're not differentiating the independent variable, you have to multiply by prime. So who did we differentiate here?
The x?
Is x independent?
No, it's dependent.
It's dependent. So what does that mean?
So we have to, I thought we have to put the prime.
You have to put the prime. What would the prime look like in this case? In Leibniz notation.
Is it dy over dt?
No, we differentiated an x.
So would it be t prime or y prime?
Dx dt. The dependent variable goes on top, right? When you have dy dx, the dependent guy is the guy on top, right? Here, your x is the dependent. He goes on top. The independent goes on the bottom. Right? So you differentiated the x, you need a dx dt. You need an x prime. Why do you need an x prime? Because x is dependent. In this one, we differentiated the y part. We left the x part alone. So you need a y prime. Over here, we differentiated a y. The y is dependent. You need a y prime. Right?
It makes sense.
So that's implicit differentiation. That's all it is. Like if you differentiate something that's dependent, multiply by the prime. If you differentiate the independent, you don't do anything extra. You do the formula. Technically, you could think of it as you're doing a prime anyway, but the prime for x would be like dx dx, right? Which cancels each other, right? It doesn't, right? If dx is always the bottom, and then when I differentiate x, I put dx on top, you don't need to write it, right? Because you're multiplying by 1. But yeah, so you put the prime whenever you have a dependent variable. Okay, so that being said, now back to this. T is the independent variable. Anyone who is not T is dependent. So this means that V is dependent. Because why is it dependent? It's not T. R is dependent. Why is it dependent? It's not T. H is dependent. Why is it dependent? It's not T. T is the independent. Okay. Now, knowing that, we're going to go through and we're going to differentiate. What will be the derivative of V? will be the derivative of v here. How fun did he disappear?
No, I'm here. I'm just thinking. So like v equals, so we're finding the derivative of like pi r squared times h, right? So
Yes,
that's
but we're differentiating the whole equation. So I first need the derivative of v. What would be the derivative of v?
So is it just one because it doesn't have any other variables? Or like,
Sure. So it's 1. So what must we do now?
oh, we have to put like dv over dt.
Yes.
Then
Now move to the other side. What do we have to do?
the product rule. So
You need
it's
the product rule because they're two separate functions. All right, so we're going to differentiate the pi r squared and then the h. How do you differentiate that?
so we first differentiate the pi r squared, which is 2 r pi times h plus.
No, you're rushing. What did we just do? We just differentiated an r.
Oh, so it's dr over dt.
You need to multiply by dr dt.
So it's plus pi r squared dr dh dt.
Yes. So that's what you have. Of course, you don't need to write a 1 here. You just, the derivative of v is dv dt, right? Kind of like how the derivative of y is dy dx. Yeah, what happened is it went to 1, but then you had to do the chain rule and multiply by the dy dx. But yeah. So you think you got it now?
Yeah, it's just that it was like so much material. Like I kind of like forgot what the implicit was. Like had
Right. Yeah. Yeah. Which is totally fine, but there's not much time before you're going to be tested on it, right? So it's not like we can wait around. Like you kind of have to. I kind of have to make sure that you're kind of keeping up the pace, more or less. So, I mean, when is our next test? It's in about 2 weeks. Right. So that's what you need to know about implicit differentiation. If you're differentiating a dependent variable, multiply by the prime. That's basically it. So differentiation, you know all the rules and all the formulas and all that, and you know the product rule, the quotient rule, all that. Great, excellent. Implicit differentiation. Oh no, what do we do now? Multiply by a prime when you're differentiating a dependent variable. That's it. That's the only change. Everything else is exactly the same. So we still had to do a product rule, but the difference is I differentiated an r. R is not t, therefore I need a dr dt. If I differentiate an h is not t, I need a dh dt. Right? If you differentiate anything that's not the independent variable, you need a prime. And that's how implicit differentiation always was. It's just that one of the variables present happens to also be the independent variable. So you just didn't see that the x was doing anything. But in this case, that's not the case. The independent variable isn't visible at all. So it literally means you have to think of everyone else as dependent. Okay. But that's actually a very important part. Like you will get the problem wrong if you don't do the differentiation part correct. But that's the derivative. So when I say, so in step 5, when I say differentiate, you have to realize it's not just differentiate, it's differentiate like with respect to time. And that actually makes a difference. It tells you that if you're differentiating anybody and it's not t, you need a prime. Okay, so moving on, we have, now it's step 6. Now step 6 we get to, it's just plug in. Right? So, because that was step 6. Now we are at the point where we can solve for stuff. So I want dv dt at a certain point. I want it when my r is 1 and my h is 3. And here's my r and here's my h. I can plug those in. I also know that my dr dt is 1 and my dh dt is 2, which means I know what this is and I know what that is. I can literally plug in everything. So here we're going to plug in. So this means that dv dt at the instant we care about, our r is 1, our h is 3, dr dt is 1, r is 1, dh dt is 2, if I recall correctly. Yes. And so this means that our dv dt, well, that's just 6 pi plus 2 pi. So this is going to be 8 pi. And its volume, so this is meters cubed per second. Yes, per second. Yeah, but I don't really care about the units, as I mentioned before. So if you just get 8 pi, you'd get it correct. But yeah, that's it. Now, again, here's the 6 steps. Read, diagram, what you know, what you want, equation, differentiate implicitly, plug in. Those are always the steps. Okay, so let's do another one. What's going on with this guy? So I think so. So complicated on this thing. Okay. So here's another problem. The length of a rectangle is increasing at a rate of 8 centimeters per second. The width is increasing at a rate of 3 centimeters per second. What is the length? When the length is 20 and the width is 10, how fast is the area of the rectangle increasing? Okay. So what do? I don't know. Panic. No, we don't. One, I realize that this is a related rates problem, so I automatically know what 6 steps I should go through. So first one is, of course, to read. All right, cool. The second one is diagram. Diagram. Rectangle is increasing. It's a rectangle, so it's a rectangle. Staples easy button. And then you're like, well, I know the length and width, so let me call this length and width. And I label them L and W because I know they're changing. So here, and I want to know the area. So A is area, L is length, W is width. So that's my diagram. 3, what do I know? What do I want? So I know the length is increasing at 8. So I know that dl dt is positive 8. Its width is increasing at a rate of 3. So I know that dw dt is positive 3. How fast is the area increasing? So what do I want? I want the rate of change of area. When do I want it? Now. No, I want it when length equals 20 and width equals 10. Four, going to come up with the equation. Equation is you want a relationship between all the variables that you just wrote down in here in the diagram. So, I mean, area equals length times width, right? And that's it. That's step 4. 5, I want to differentiate. Now I'm going to just write differentiate, but we know that it has to be implicit with respect to t. It is always implicit with respect to t. Just in case it's not here, it's not clear, always. T is always the independent variable when it comes to related rates. Okay, it's never going to be one of the other guys. It's always t. So now we're going to differentiate here. Obviously, I need the product rule because these are 2 variables. Any other variable I see that's not t, it's dependent. So I have to think of all of these guys as functions. So I have L, which is a function, W, which is a function, and they're multiplying each other. I need the product rule. So I'm going to go through and differentiate. Derivative of A, dA dt. Because I have to differentiate A with respect to t. Derivative of L times W, differentiate the L, leave the W, I need to multiply by dL dt. Because I just differentiated L. Plus, leave the L, differentiate the W, I have to multiply by dW dt, because I just differentiated the W. L is not t, W is not t, A is not t. If I differentiate them, I need to multiply by d of the variable over dt. And that's it. 6, plug in. So this would mean that dA dt, which is the guy we want to find, is going to be equal to W, which here we know W is 10, times dL dt, which is 8. L is 20. dW dt is 3. And that's all she wrote. dA dt is equal to 80 plus 60. So dA dt is equal to 140. This is centimeters squared per second, because it was centimeters per second. Okay, so that's that one. But again, same 6 steps. Read, diagram, what you know, what you want, equation, differentiate, plug in. Always. Okay, so, and t is always the independent variable. Here's a third one. A 15-foot ladder rests against a vertical wall. Suddenly and without warning, Batman starts pulling the foot of the ladder along the ground away from the wall at 2 feet per second. At what rate is the ladder, the top of the ladder, sliding down the wall when the foot of the ladder is 9 feet from the wall? Okay, so again, at this point, we just know about a ladder. Batman, for whatever reason, is like pulling the foot of the ladder. Maybe the Joker was running up the ladder. He's like going to pull it down and he's going to fall. And, you know, hopefully he doesn't break his one rule, whatever. All right, so that's the situation. So it's kind of a weird situation, but then I realized, oh, they told me the rate of change of something, right? They told me the foot of the ladder is running against the ground at 2 feet per second. And then they asked me at what rate is the top sliding down? So clearly there's a relationship here where they're telling me a rate of change of one thing and they ask me for a rate of change of another thing. It's related rates. All right, cool. So 1 is your read. 2, diagram. Okay. What is the diagram here? What does the diagram look like?
You have a ladder against a wall.
Yeah, so what would the picture look like?
It would look like a triangle, a right.
Look like a triangle, right? So you have like a wall here. It's the vertical wall. You have a ladder lying against that wall, so that's the ladder here. And then of course, you know, there's the ground, which the ladder's on, right? So you already have like this right triangle diagram coming in, right? Because the vertical wall, and we're going to, of course, assume that the ground is horizontal. I mean, why not? All right, so now here's the thing. How would we label this diagram? How do you want to label it? What do you want to label the height? Well, I can call this X, I can call this Y, because it kind of reminds me of the XY plane. What do we call the hypotenuse? What do you think? Yeah, 15. Okay, now, there are a lot of students who don't pay attention to this rule and they would label this with another variable like Z or something. And technically nothing would be wrong with that. And technically you would still get the problem right. But statistically, most students who take that, do that, end up getting the problem wrong. And I'm going to show you why later. So this is the right triangle, and that's the proper labeling. Anything that's not changing, label with a constant. Anything that is changing, label with a variable. It's a 15-foot ladder. It's always going to be a 15-foot ladder, right? It's a ladder. It's not going to change. However, Batman is pulling the foot of the ladder away from the wall, which means that this X, this length here, is not always the same. It's extending, right? So that's changing. Now, as this is being pulled away, the top of the ladder is moving down. So this length here is also changing. It's actually getting smaller over time, which means the horizontal length is changing. It cannot be a constant. It must be a variable. And the vertical length is changing. It cannot be a constant. It must be a variable. However, the hypotenuse is a ladder. It's not changing. It's always going to be whatever length you started with. So that is 15. So that is our diagram and properly labeled. Now we move on to 3. What do we know? What do we want? Okay, what do we know? I know that the Batman is pulling the foot of the ladder along the ground away from the wall at 2 feet per second. So that means X is moving. So this means dx dt is +2. And it's +2 because X is getting larger. i.e. increasing, which we now know what that means. Something that's increasing has a positive derivative. So dx dt must be positive. So by reading carefully, I realize, oh, Batman is pulling it away. I have a diagram to set it up. All right, I realize that if Batman is doing this, this is how the diagram is going to respond. That's getting longer, which means that this needs to be a plus sign, right? Like, this is why you read. It's very important. Reading is fundamental. Okay, so because just that one sentence has a lot of information being given at once. If you're not careful and you're not reading closely, you're going to miss it. So yeah, what do we want? We want how fast the top of the ladder is sliding down the wall. Well, that's dy dt. When do we want it? When x equals 9, right? When the foot of the ladder is 9 feet from the wall. All right, so that's what we know, what we want for equation. What's the equation here that relates all my quantities?
Is it the Pythagorean theorem?
Pythagorean theorem, right? So the sum of the squares of the legs is equal to the square of the hypotenuse, right? So this means that x squared plus y squared equals 15 squared. All right, cool. 5, differentiate. All right, what's the derivative of this? Derivative of x squared.
2x dx dt.
Right. And y, obviously 2y dy dt. What's the derivative of 15? 15 squared. The square is there, so what do we do?
Wouldn't it just be 0? Because
It would be just be 0, right? So just want to make sure you know that, right? It's a constant. It's 0, and I'll bring it up later. So now we go to 6. All right. So everything seems fine, and we're going to move on to the next step. Plug in. All right. Cool. What do I actually want? I want the dy dt, right? So this is actually the guy that I care about here. So I mean, I could even solve for him. He's going to be dy dt. I can divide both sides by 2. I'm going to move the x over dx dt over y, right? And now I can plug in, right? So I know that x is 9. I know that my dx dt is 2. And my y I know is wait, they never told us why. Oh man, I don't know what to do now. Did Jhevon make a mistake in the problem? Like it's probably a typo. Did you want me to typo? I'm already under pressure. You can't. No, there's no typo. The y was left out on purpose. What do we do when something is left out on purpose? Well, I mean, I read the steps very quickly, so just make sure that you know how to read it. At first, you may end up with several unknowns. In this case, you should be able to go back to the equation in step 4 and solve for the other guys. So whenever you're in this situation where you realize, oh, something's missing, what you do is you go back to step 4. Now, in step 4, you have that equation, x squared plus y squared equals 15 squared. Right? Now, we know that x is 9. We don't know why, but now we have an equation where y is the only unknown. We can solve for y. Okay, who can tell me what y is without actually squaring 15 and 9? And then taking a square root, like 15 squared minus 9 squared. Let me give you a hint. 9 is the same as 3 times 3. 15 is the same as 3 times 5. Does that help you to know what the y is?
Is it 3 times 4 squared?
It's 3 times 4, right? And that's something that you know from geometry. It's a 3, 4, 5 triangle. Right there, this is a Pythagorean triple, a very popular Pythagorean triple, as is something like 7, 12, 13, right? So there are some numbers that go together with right triangles. So you can automatically know that y must be 12. Now, because we have a 3, 4, 5 triangle. So little tricks like that, similar triangles, 3, 4, 5 triangles, Pythagoras' theorem, little tricks like that is what, when I said, oh, you should remember your geometry, it's stuff like this that I'm talking about. Now, of course, yes, you could go through and square the 15, subtract the 9 squared, and then take a square root, but you're not supposed to use calculators technically, and yeah, that would just be too much work. But here you could actually eyeball it. It's a 3, 4, 5 triangle where it's proportional. Each side is multiplied by 3. So the missing side has to be the side corresponding to 4. And so, yeah, once we do that, we figure out y is 12. Then we go back here. Right, so now we know everything. Now we can figure it out. We have dy dt equals 9 times 2 over 12. And 2 into 12 goes 6, 3 into 6 goes 2, 3 into 9 goes 3. So this is going to be minus 3 over 2 feet per second. Now, I want you to appreciate this minus should be there. If you don't have a minus, you did something wrong. Y is decreasing. So your answer should have a negative there. Right. What I want to do now, before moving on, is just mention something that's technically not wrong, but an issue that could happen. Like, why did I recommend that if something is constant, label it by the constant? So here is, this is something that's not wrong, but a potential issue. If you had that and you're like, okay, this is X, this is Y, this is Z. So this is the thing that's out of place. Now, why is that bad? It's not necessarily bad. You're going to move down and you're going to be like, well, it's X squared plus Y squared equals Z squared. And then you're going to end up, okay, dx, 2x dx dt plus 2y dy dt equals 2z dz dt. Now, here's the issue. Students often don't know how to deal with these guys. Which is where my recommendation comes from. Now, if you think about it a little bit, you will know what these are, but usually on a test when you're like freaking out and you're like anxious and you're just trying to rush through a problem, they get here and they get stuck, right? You know, they can't handle it. They can't handle the truth, right? However, technically, even if you got here, you should know how to handle it because Z is representing the ladder. The ladder is not changing, which means dz dt is actually 0. So this whole side would actually wipe out and become 0, and you would actually get the equivalent of this, right? But they get here and they see these z's, they see dz dt, they don't know what y is. There's like a bunch of unknowns. Like there are like 3 unknowns in this one equation. Like how am I going to get past it? But they just don't remember those little things. Like, well, it's a ladder, it's 15 feet, it's not changing. Something that's not changing means the rate of change is 0, therefore the derivative is 0, right? That line of thought would be how you get through, that's the solution. But for whatever reason, students never really come across that. As well as going back here, when you plug in x to get 9 squared plus y squared equals z squared, again, students get confused by this z. Well, what should z be? And then, you know, especially when they didn't read the problem correctly and they don't realize, oh, the z should be 15. And then they're gonna, like, it's like you're putting yourself through some extra hoops here mentally, which, I mean, they might not seem like a big deal now, but on a test, they're a big deal, right? So you have to realize what a lot of students don't realize, which is why they get in trouble. Like when I tell students, oh, proper notation, write your parentheses. And they're like, well, I know the parentheses should be there. Like, dude, we're not studying for you who right now you're calm and you know the parentheses should be there. We're studying for the version of you that's going to be stressed and anxious under testing conditions. That's the guy we need to study for, right? So you need to remember, like when you're calm and everything's there and we're like having a conversation, things will occur to you now that won't occur to you under a stressful situation. You need to make things as easy as possible so that even when you're under stress, you're still getting things right, because you set things up in such a way where you don't have to think too hard about it. And just by labeling this thing a constant, I never end up in the situation where I have to figure out, well, what is z? What is dz dt? Like I never end up in that situation, which, I mean, at this point, it doesn't seem like a big deal, but I can tell you because from experience, I know, like I've graded thousands of calculus papers by now. And I can tell you, students who go this route and just label everything by a variable x, y, z without thinking about it, they end up getting stuck here. They end up getting stuck at almost the last leg, step 6. They're almost there and they're like, they can't get to the answer. And it's not because they can't figure it out. They're anxious and they just didn't, they weren't doing things as efficiently as possible. So yeah, so that should be something that is kind of, you should kind of be aware of. There are some times when I give advice on something and people are like, well, yeah, but you know, you didn't have to tell me that, I would kind of know. The point is, I'm not telling you the advice. I'm telling the version of you who's stressed and under a very stressful situation the advice. That's who the advice is really for. It's not really for you who's sitting here right now, but it's for the other version of you, the version of you when your brain triggers the flight or fight mode. That guy is not going to remember the parentheses. He's not going to remember that dz dt should be 0. So just don't put yourself in that situation. Label it with a constant if it's not moving. Okay, let's do some more. Maybe do a couple more. Ugh. I don't know if I want to go through that one at this point in the night. Okay, let's do 9 before 7. It's not that bad. 9, we're going to have to remember some other concepts from geometry. So I'll probably do this, leave 9 for you to try, and we'll do it next class, which is all the way over next week. You'll have time to try problem 9, as well as the rest of the problems on this page. You really should try them. But yeah. A man walks along a straight path at a speed of 5 feet per second. That's a really fast, it's a really fast walk. That's 5 feet per second. Yeah, that's, I mean, I don't even know if it's possible to run that fast. So let's keep going. I mean, it's probably possible to run that fast, but yeah, that's a very fast gate. A searchlight is located on the ground 16 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 12 feet from the point on the path that's closest to the searchlight? A couple things you have to remember here is that the point closest to something is the point that's at a perpendicular distance from it. So that's talking about the perpendicular distance. So one we're going to read. We know this is a related rates problem because they tell me the speed at which the guy is walking, and then they ask me about the speed at which the light is rotating. So it's a related rates problem. Now, two, need a diagram. So we have a straight path. So that's the path. Here's the guy who's walking. And here's the searchlight. Okay. Now the searchlight there's a beam of light focus on the man. So this is like the light beam. And we're told that the searchlight is 12 feet from the point on the path closest to the searchlight. The point on the path closest to the searchlight is the path that is at a perpendicular distance from the searchlight. So that is 12 feet. So of course here, you realize that this distance that the man is from that point is changing because the man is moving. So we can call that something, call that, say, X. Now, as the man moves, like he's over here, what's going to happen is that beam is going to get longer. So this length here is also changed. So I'll call that Z. Now the searchlight itself isn't moving, so that 12 feet should be 12, stays 12. So this is the triangle. Now, something else they mentioned. At what rate is the searchlight rotating? So now then they say rotating, that's kind of different, right? That's it's not about angle. It didn't talk about how the length of the light beam is changing or how the length of something else is changing. It's talking about the angle. So there's this new variable right here that I care about. So now we're in a situation of, yeah, how do we actually get this? This is 3. What do we know? Well, I know that dx dt is 5. What do we want? I want d theta dt. When wait, this 12 was 16. At what rate is searchlight rotating when the man is 12 feet from the point of the path closest to it? So that's x is 12. See, read. Okay, so now, yeah, that's what I know, what I want. So for equation. So now here's the thing. The z, it definitely is a part of the problem, but it kind of doesn't even come into play here. No one told me anything about the z. So I can't actually ignore the z, right? Now, technically, we could find this information, but it's too much work to find it. You'd have to do another related rates problem to find that. So the idea is, let's not do it. Let's just ignore Z. Like we don't actually need it. Right. So now we're in a situation where, can you think of an equation that would relate theta and x? Tangent, right? SOHCAHTOA, right? So you have to remember SOHCAHTOA, right? This side here is the opposite side, and this side here is the adjacent side. So SOHCAHTOA, right? So that's the equation. Tangent of theta is going to be equal to x over 16. So now we go down here. We're going to do differentiate. Anyone remember the derivative of tangent? So the derivative of tangent is secant squared. Now I have to put d theta dt because it's not t. And derivative of x over 16, well, that's just 1 over 16 dx dt. So this would mean that my d theta dt is equal to dx dt over 16 over secant squared. Right, so now step 6, gonna plug in. Dx dt I know, d theta dt I don't know, secant squared theta. So dx dt, I know that's 5, I believe it was. What's secant squared theta? Well, we don't know. What do? Panic. No, we go to step 4, which says tangent of theta is x over 16. And so this means that tangent of theta is x was 12. Yes, we want x is 12. Tangent of theta is 12 over 16. So tangent of theta is 3 over 4. So that's your tangent of theta. So what that means is that you have a right triangle where the opposite is 3, this side is 4, which means obviously that side should be 5. It's a 3, 4, 5 triangle, which tells you that the cosine is going to be adjacent over hypotenuse, which tells you that the secant is going to be 5 over 4, which tells you that the secant squared is going to be 25 over 16. And then you move that back up. So you have d theta dt equals 5 over 16 divided by 25 over 16. The 16s are going to cancel. You're just going to get 1/5. It's like rad per second. Yeah, that's that. Now, there was a problem that I worked out that I wasn't going to actually cover, but I actually already worked it out over here. So I was just going to copy it and paste it. So you can look at that as an extra example. But then I want you to try the other ones. Let me actually kind of tired of fighting with the iPad to copy that thing. Okay, so that was problem 8. Read diagram. This diagram is kind of tricky. Well, you know what you want, equation, differentiate, all that good stuff. 3, 4, 5 triangle comes up again. And yeah, but what I want you to do after this is try this and the others for next class. And that is, when I say this, I mean this guy. Okay. But we are going to stop there. Related rates, important application of derivatives, but it's about finding the rates of change of something that you don't know directly, but you know about the rates of change of something that's connected to that thing. So you can use related rates to find the rates you care about. So we did example 1, 2, 3. We skipped 7, gave you the solution for 8. Asked you to do 9. We did 9. I asked you to try 7. And try some of these other ones if you want. Or you should. Salfan was saying, it's hard to keep up in the summer, and I am aware of this, but it means you have to work extra hard. But yeah, that is where we're going to call it. So next time I'm going to finish up this example, and we will do, I think we'll move on to talking about maximums and minimums again. But I gave you a lot of background that's going to help there. So it should be an easier discussion. And yeah, it's all she wrote. So we will stop there. Thank you for your time and attention. Yes, I remember office hours. And yeah, I think use the same link that I sent you earlier. I'm going to try and open it. If not, I'll send you a new link, but it should still work. Yeah, we'll stop there. Thank you for your time and attention, and I'll see you in the next one.